talk about the vertical drop, which is easy enough to demonstrate and looks as though it's a simple form of, or simple effect of gravity. But in fact, it's much more difficult to explain than, for example, a circular orbit of a planet or a moon, or even an elliptical orbit. The vertical drop is quite difficult to explain. What's difficult about it is explaining why the body begins to fall. To do that, I'm going to have to go into a little bit of mathematics. The potential energy between two bodies, whether one's above the other or not, is not the point. The reason why this falls is not because it's vertical, it's because it's toward the center of the Earth. If we were on the side of the Earth, of course we would be standing, pointing out, and down would be just as it is here. But if you can think of looking at the Earth, someone standing on what we would consider to be the side, then gravity goes that way. So it's between the two bodies, not necessarily, and which defines up and down. Up and down is not an absolute direction. So I'm going to draw it like this. The potential energy between those two bodies depends upon its distance. But if this body is moving, it's not moving, of course, before I drop it, but if it were moving, then there would be some kinetic energy, and we can depict that by showing it at a perpendicular dimension, because it's a different form of the same thing. That would represent the kinetic energy, and this would represent the total energy. Now, this is what's called a mathematical model, and we can now derive an equation to show that the potential energy, which is proportional in this case to r squared, because this is r, call that r, proportional to r squared, and the proportionality can be expressed by the product of the masses of the two bodies, because that multiplies the force of gravity which exists between the mass of the bodies, and the mass of each body increases the gravity. This number represents the number of lines of force, if you like, between the two bodies. So that expresses the potential energy. There's a similar expression here, but here it's not the distance that we usually use, it's the velocity, and the v squared. This is what I'm going to just put v there for the moment. This is the energy, or what's proportional to the energy, and there are different units you'll see there, distance and speed. So I can convert this into a speed by dividing by a time, which we call a period of the system. And that represents the total energy, which, if this is called a distance of r naught, is m r naught squared. So there's the equation that shows where you can add the two velocities in this particular model. Now, it's not difficult to see that if you multiply both sides by the period, you get that the mass times the r squared plus mass times v squared t squared is equal to the total energy. This would of course have a t squared underneath it, r squared here. So you can see that we can use either velocity or distance to represent energy. And this is what's called an equivalence. That a distance is equivalent to velocity when you're talking about energy. We also know it's equivalent to mass, but that's another subject. So I'm going to now use that to explain the vertical drop. That for every time you speak of the energy as a potential energy, you can speak of that energy as being kinetic energy. So that if I take a body, say at this height above the center of the Earth is down here, and I raise that body, I give it a height, and that is equivalent to the, or representative of, the potential energy. When I stop at the top, raise the body from here to here, what's happened to that energy? That energy is not potential energy, but it can also be expressed as a kinetic energy. In other words, I can say that the potential energy is equivalent to the kinetic energy. But kinetic energy involves movement. Where's the movement? Well, the answer is that the movement is in a dimension that is perpendicular to space, which I've referred to before, and it's called the x dimension. And the body has a velocity in that invisible dimension equivalent to the energy, the potential energy. So the value of x is equal to v squared t squared, or rather vt, because we're going to square it when we add it. The actual value of x, the displacement in x, the separation between the bodies in the x dimension, is equal to vt, and when you square that, you get the energy. This is vt, this is r. When you square that, you get the equivalent kinetic energy to this potential energy. And then they're not both present at the same time, so you can't add them because you have either one or the other. So that the potential energy between the two locations of the body is equivalent to the kinetic energy. And when this body has been raised from here to here, it's now got velocity, which we can't see, in the x dimension, which represents its potential energy. Now you may say, if it's moving, why isn't its location changing? Well, there are two ways of explaining that. One is that the dimension is invisible, therefore we can't see any movement in it. The other is that it's not free to fall. It's not really a separate body as long as I'm holding it. It's only when I release it, it's free to fall. And then it then moves in the x dimension, and this, as I've shown in previous videos, causes it to rotate with a constant total energy down to here, where it then falls to this point. But while I'm holding it, it's not free to fall, which means it can't be moving. And the reason for that is because by holding it, I am covering its mass. I am increasing its mass to an effectively infinite amount, so that its momentum, mv, P equals mv, this is momentum. By my holding it, I'm making its mass infinite. It can't move, and its velocity is zero. And but it still has the momentum, and this is the interesting thing. You raise something from here to here, it has momentum in this direction, or in the x dimension, which we can't see, but it's not moving because it's unable to move. I have effectively I've taken away its freedom to move, I've increased its mass. But when I release it, its mass now is free to move, and it moves and falls. Now that was difficult to explain. I'm sure it was difficult to understand, but that's the problem with the vertical drop. It's not a simple case at all. Well, I hope that's helped to some extent. We'll talk later, I'm sure, about it again. Thank you for watching.